Alex Dadgar is going to talk about Nomad, and in particular, how placements find their new life. Right, Alex? Come on up.
I'm Alex Dadgar. I've been at HashiCorp for a bit over a year and a half now. I've been working on Nomad since before its public release, so it's been a while. It's dear to my heart. For those of you who aren't familiar with Nomad or cluster schedulers in general, or for those of you who are, you might have an idea what we're going to talk about given the tongue-in-cheek title. But for those of you who aren't as familiar with cluster schedulers, what they do is they take a set of nodes which comprise your cluster and a set of jobs. And it's the duty of the cluster manager to make the placements of the jobs onto the associated nodes and to do this in an intelligent fashion. So really, the inputs to a cluster scheduler are a set of jobs and nodes, and it acts as a function to make placements onto those nodes. It is a little more complicated than just a one-to-one mapping because not every node or job is the same. A real cluster has a heterogeneous set of nodes. Some might be 2 cores, some might be 16 cores. Some might have 10 gigabyte solid states just to start up, while others might be huge multiple terabyte data storage nodes. Further, jobs have different runtime requirements. Your big Java app might need multiple gigs of memory just to start up, while a small internal dashboard might just need a few megs. So we want the cluster scheduler to map jobs to nodes that can best match their requirements. So today we're really going to take a deep dive into this black box that is this mapping function and see how Nomad makes these decisions. Before we do that, I'd like to briefly go through the job file, which is the input to Nomad that describes the job and its requirements. So this is a simple job file that you could actually give to Nomad and it would run. It defines a job named Redis. There's a single task in it. And it's incredibly simple to read and write. Critically, the job file in Nomad declares what to run. It's Nomad's job to determine how and where to run this thing. So if we come back to this simple job file and examine it a little more closely, we can see that it describes multiple data centers. So we say data centers equals an array US East 1. That array could enumerate more data centers. So Nomad is multi-DC aware out of the box. We can also look at the bottom of the file and we see a resource block. This describes the requirements of the task. So this one's saying it needs 500 megahertz of CPU, at least 256 megs of RAM. And it's Nomad's job to find a node in your cluster that can guarantee this task those resources. Next, we see driver is a string. In this case, it's Docker. But Nomad supports more than just Docker. We have multiple containerization technologies supported, so Docker, Rocket, and LXC currently. We also support shipping of standalone binaries. So if you have a binary, maybe Go, C, you can just ship that. And what Nomad will do is it'll build a lightweight Linux container for you and employ many of the same technologies as Docker. So we'll build the isolated file system for you. We'll put it in a C group. And we'll make sure that you don't have interference between multiple tasks. This is really nice. We can also run VMs for you, et cetera. So this is a very simple job file. But right now, pretty much the only restriction we've given Nomad is that it must run in US East 1. Well, we can kind of narrow and restrict where you can run jobs using something called constraints. So here I added a constraint that what it does is it says, I only want this job to run on M4 extra large instances. So now when Nomad gets this and it's trying to decide where to place things, it'll ensure you get it on an M4 extra large. So this is a pretty simple constraint. There's other cool ones. Let's say we want to run 3 instances of Redis, so we have some scalability. We can add a constraint called distinct hosts. What this will do is, as it places multiple instances on your cluster, the scheduler will ensure that no two instances will end up on the same machine. So if a machine dies, you'll only be having one go down, transiently, of course, but still, this will give you some more availability. Another cool thing you can do, let's say you're running in a private data center. Your operators could annotate your nodes with metadata. So you could say, this node exists on this particular rack. And we introduced this new constraint called distinct property recently. And what you can say is, as you place these 3 instances, I want you to spread them out across distinct values of this particular property. So in this case, when you schedule 3 instances of Redis, it'll place it on 3 unique racks. So even if you have a NIC failure or a power outage on a particular rack, you still have uptime. So that's an incredibly simple job. It's functional, but what in that file impacts placement decisions that the scheduler has to actually think about? Well, the first one is the set of allowed data centers. That constrains the set of eligible nodes from the get-go. Next is driver type. Not every node will have the same drivers as every other node. So if you have a mixed cluster of Windows and Linux machines, and you're trying to schedule an LXC container, obviously the scheduler has to know, hey, I can't send that to a Windows machine. So that affects placements as well. Constraints obviously impact placement decisions, since operators are explicitly constraining the nodes that it can run on. Also, the resource requests. So in that example, we just asked for 256 megs of RAM. Hopefully, every node in your cluster can provide that. But you might be running a database or a very large app that requires more resources than some of your nodes might have in aggregate. In future releases, we'll have GPU support as well. And it's likely you're not paying for every node in your cluster to have a dedicated GPU. So the scheduler has to be able to match those resources to nodes that can provide it. So that job is incredibly powerful. We expressed quite a bit, and what I fit in one slide. So we try to keep it simple. That's pretty core to Nomad's philosophy. Cool. So now that we understand the input to Nomad, we can kind of start diving into what Nomad does to make a placement decision. So when I submit this job, there's multiple Nomad schedulers running in parallel. We won't go into that, but a single scheduler will take the work of deciding what to do for that job. And what it immediately does, it looks at your cluster and tries to reconcile with what already exists. So if I had this Redis job, I might have submitted it already with count equals 1. And now I'm upping it to count equals 3. So the scheduler will look out and be like, there's already 1 instance of Redis, so I only need to place 2. Similarly, when you're scaling down, it'll detect that it needs to stop certain instances, so I'll just stop those. And it can also do in-place updates for certain things. Let's say you're add a tag to your console registration. It can just do that without doing new placements. And it can also do rolling updates of your services. So it can do all of that, but what we're really going to deep dive into is how it goes through and decides where to place each new allocation. So the way we do that is something Nomad calls the stack. So for every placement the Nomad needs to do, it constructs what we call the stack. So in that example job file, when it count equals 3, if it needs to place 3, we'll construct the stack 3 times. The stack is composed of simple iterators that are chained together. So each element of the stack just has a simple method called next, one function. At the bottom of the stack, which is the iterator that feeds through all the rest of the stack, is a node source. And the scheduler calls select at the top of the stack. And the output is one highly ranked and eligible node in the cluster. So in that job file, there was a constraint. When the scheduler calls select, what will come out is what the stack thinks is the best choice for placing one instance of that stack. And once it decides to use that node, the next time it calls, the next node that will be returned is the next most highly eligible task. So we're going to use this job file as an example to walk through what happens inside of this stack so we can understand it. Each element is pretty simple, but composed you get pretty complex behavior, which is nice because it makes it adding features and agility to the scheduler pretty easy. So we're going to start with data center equals US East 1. And we're going to assume that we have a Nomad cluster managing 2 data centers out of the box, US East 1 and US East 2. So we'll construct the stack, and we need to initialize the node source, which feeds the rest of the system. Nomad will have all these heterogeneous nodes in multiple data centers. Excuse me. And what it'll do is it'll just examine the job file, detect what data centers it has, the job says it's allowed to run in, and it'll just throw away everything that's not in that eligible set. What it does next is it shuffles all the nodes. So subsequently, anything that accesses this iterator is seeing a randomized set of all eligible nodes for that job. And this is important because, as I mentioned, between multiple placements, we'll call the stack multiple times. So we want to see a random representation of all eligible nodes in that cluster. Cool. The next one is we need to make sure that the node we select has the Docker driver. So this is pretty simple as well. We have a driver filter that reads those randomized nodes. And when it gets called next, it'll read behind it, get a random node, and only allow nodes that have Docker through. So in this example, if we assume every little node has Docker, it'll filter only the little nodes through. Similarly for the constraint. So in this one, we're saying we only want to schedule instant types M4 extra large. So we'll instantiate a constraint filter that reads from the previous iterator, and it'll just only let nodes that are M4 extra large by examining the node metadata. So in this example, if it's only the orange nodes, now we've filtered through 3 simple iterators. We've gone from multiple data centers to just US East 1, to nodes with Docker, and to nodes that are M4 large through 3 composed iterators that are pretty simple by themselves. So that was one constraint filter we saw. Nomad has multiple. So the one we saw was a regex matcher, but it was a very particular one. It was an exact match. But we could also do something a little more complicated. Let's say I don't particularly care if it's an M4 extra large, but I want it to be of the M4 class. I could do this regex that says, I want M4 with any number in front of it extra large, so it could be a 2, 4, 10, or 16 extra large, and it would only let those nodes through that constraint. We also have a version filter, which is nice for things like Java or ensuring that you're running against a particular version. So I could say, I don't care that I'm running 1.81 of Java. I just need the feature set of Java 1.8. So please run me on a node greater than or equal to that. We also have distinct hosts and distinct property, which we covered. The interesting thing about these 2 iterators, unlike version and regex matcher, is they're somewhat stateful. So regex matcher and version, a node comes in, it applies the same function no matter what's happened in the system. With distinct host and distinct property, its decision to let something through the filter is affected by prior decisions. So we can go through a little example. Let's assume these nodes are annotated with their rack, and we have that distinct property on the rack. Well, when we're first letting things through, the distinct property filter has seen nothing, so it'll let 11 through. And then it similarly let 13 through. But since it's storing state on previous decisions, it can now say, hey, when I have this next one coming in that's also on rack 13, it can do this lookup and be like, I already let something through, and it's been placed by the scheduler. So I shouldn't let it through. So the next one I'll let through is 12. So by attaching state, we can get some more complex behavior out of these iterators. And that's actually it. So with these 3 simple iterators, we have met every constraint of the job. US East 1, Docker, it's M4 extra large. So we can use any of them. But now the question is, do we use this one, maybe even this one? They all look the same. So how do we decide which one to actually use? The reason they all look the same at this point is, as we've been going through the stack, all we've gone through is the eligibility steps. So we've just filtered the original set of all nodes Nomad is managing to the nodes that match those eligibility steps. We still have to decide which is the best node to run on. So what we do is we leave the filtering steps of the iterator, and we enter the ranking steps. So, the ranker can also filter nodes, similarly to the filters, where it looks at the node and decides to drop it or let it through on to the next iterators. But what it can also do is annotate the node with a score. So yeah, we'll go through that. So the two rankers we have right now are the bin packer and a job anti-affinity ranker. And more likely will come. The one that's going to be the most obvious is for job operators to supply their own affinities. So you might say, I don't particularly care that I'm in a particular data center, but I would like to be in that. So if you can put me there, or I would like to run on this machine instance, but if you can't place me, don't fail to place the job. I just have a preference. So we can start ranking nodes according to those preferences operators give. But we'll start with the bin packer. So the bin packer has 2 jobs. It filters nodes that can't fit the placement, meaning not enough resources, and score nodes based upon their density. So if the bin packer had these 3 nodes and it had to place this job, where each of the colored squares indicate a prior placement, well, it could try to place on node 1, but obviously that doesn't fit, so it would filter it. So now we actually just have 2 nodes to consider, node 2 and 3. Both of them can obviously fit the job, so now the ranker is responsible for assigning an initial score to these 2 nodes. So anyone have any guess which one would get the higher score? 3, 2, 2? Yeah, it would actually be 2. So there's 2 questions to really ask: how it gets a higher score and why it gets a higher score. So we'll go through the how first. When a node first joins the cluster, it'll connect to the servers, and what it'll do upon initialization is fingerprint the host. So it'll reach out and detect how many CPUs it has, what clock speed that CPU is, how many gigs of memory does it have, etc. It'll go through all of this and then send that information up to the schedulers. So the scheduler has knowledge of every node's overall resources. So for the filtering step, it's pretty simple. What you do is you take everything that's on that node already and what you need to place on that node, and you add up the resources, and you ensure that that is a subset of the node's overall resources. So and it also an operator could annotate the node and say, you might detect that I have 16 gigs of RAM, but I have a Datadog monitoring agent on the node as well. So I'm going to reserve 2 gigs of RAM for the operating system and that monitoring agent. So Nomad only used 14 gigs. So I'll also take that into consideration. So next, what it does is after it's filtered nodes that can't even fit the new placement, it wants to produce a rank for that node, ranging from 0 to a maximum score of 18, where 18 is a more desirable node. So the algorithm we use is actually inspired from a Google talk where they were examining the impacts of various ranking algorithms in their own Google data centers. So the algorithm we used is pretty simple, but it provides a nice behavior. What it is 20 minus 10 to the x minus 10 to the y, where x and y are the percent free CPU and memory. So completely utilized CPU would be 10 to the 0, which is 1, and similarly for memory. So a completely utilized node would be 20 minus 1 and 1, so you get to 18. And 10 to the 1 would produce 10, so you would get a max score of 0. So that gives us our range. What this scoring function looks like is something like this. It's polynomial on 2 variables, so the behavior you get is the scores increase fairly rapidly when both of them become highly utilized. So we see that towards the 0 on both axes. And what's nice about this function and why it works particularly well is you can't achieve a particularly high score if you're only maxing out a single dimension. So even if you're fully utilizing CPU, but you have a huge amount of unused memory, the score of the node won't be particularly high. It'll only be like 8 or 9. Someone can do the math. So what this function does is it optimizes for overall utilization of the node. So you try to get the most out of the money you're paying to actually have that node running. So that's how we do this. The question of why really breaks down into bin packing versus spread. So these are the 2 most common algorithms schedulers will use. Why we pick bin packing is really for 3 reasons. It's better at accommodating heterogeneous workloads. It's easier for operators to do capacity planning. And in the future, it makes auto-scaling better. So we'll go through each. So what we'll do here is we have a set of tasks or jobs we need to place. So we have 2 3 GB tasks and 2 4 GB tasks. And we'll examine what happens under the 2 algorithms, bin packing and spread. With bin packing, what we'll do is we'll place the 2 4 GB nodes co-located with each other because that achieves the highest density. So it'll have the highest score. So that would be what the scheduler wants to do. And then subsequently, I'd place the 2 3 GB tasks together, and it would leave one of the nodes fully unutilized. So this would be the optimal arrangement of these tasks given bin packing. For spread, you would instead see something like this. You would place the 4 GB node task, and then since you have unutilized nodes, the next one would be put on an unused node. And lastly, the 2 3 GB nodes would be co-located because that's a better arrangement than a 7 4 3. So these would be the 2 steady states. The problem is when you now need to schedule a new task that requires 6 gigs of RAM, something that a heterogeneous workload, really. With spread, since it tried to get maximum utilization out of each node before moving on to the next, it can just slot right in. With spread, not so much. It can't quite cope with these heterogeneous workloads. It would be fine if every job that you were scheduling had the exact same requirements, because then you would just go through layering up each node until each node subsequently got full. But in practice, that doesn't apply, let alone in theory, and practice. Because would you give your Spark job that's doing machine learning the same resource ask as a little Tomcat server? Probably not. So it doesn't really apply. So that's why one of the reasons bin packing is nicer. Next is easier capacity planning. So assume you have 10 nodes and you've submitted a steady state of jobs to the scheduler that take up about half of the overall resources of the nodes. With spread, you would see a distribution like this. So we have each node and their utilization. So you would want to see something roughly around 50%. With bin packing, you would see something closer to this. You would try to utilize each node before moving on to the next. So you would get closer to 70 to 90% utilization. Obviously, as you get closer to 100, it's harder to find a job that will slot in. So you shouldn't expect 100% utilization. So you'd see something like this. Well, you'd notice that you have multiple fully unutilized nodes, And if this is our steady state cluster, we've submitted every job we need, well, you can see that, hey, I'm not actually using these nodes, so you can scale the cluster down. And since the scheduler will try to fill each node, it makes it easier to do projections into the future. If you know, hey, I'm onboarding one Spark job now, and I think I'll open it up to 20 more people, you can say, well, this is the load I have. The scheduler will fill each node. I can now plan my capacity. With spread, it's a lot harder because you look at your cluster and every node is utilized. So, oh, I guess I need to double my cluster, right? So that's why it's easier to do capacity planning. So Nomad doesn't currently do auto-scaling, but that's kind of the dream of cluster schedulers. You give it access to your cluster, and it'll scale it up and down to meet your resource demands. So we want to think about how Nomad will do this, and that's one of the reasons we pick bin packing. So let's come back to this example. We assume a steady state cluster. We've scheduled all these jobs. From the get-go, spread is using one more node than bin packing because it didn't utilize the nodes from the beginning. So when it needs to place the 6 GB job, it didn't have room. So let's say we now submit another job to the cluster that also requires 6 gigs of RAM. Both strategies don't have anywhere to put this node, so they'll both have to scale up. But what we see is a compounding of waste now under a heterogeneous workload as we submit more and more things. Bin packing, since it originally tried to get the highest density out of each node, is roughly wasting 15% versus 35% waste and a full extra node that you're now paying for. And this also applies when you're scaling down. The theme really is that you're paying for things you're not using. So when we scale down, let's assume we've submitted all these jobs, and some percent of them are batch jobs, and some are service. So your batch jobs will eventually finish. We can say these ones have finished and left the cluster. That'll now look something like this. The scheduler can then detect that I have unutilized nodes and scale the cluster down so that you are only paying for resources you need, plus maybe some threshold. So both will scale down, and now they both look identical, right? Well, not quite, because spread, this is its ideal arrangement. This is its best placement. Each node is roughly equally utilized. But with bin packing, there's a better arrangement. The scheduler can detect this 3 GB task can also be co-located with the 4 GB task, and that would give you a higher score for that node. So it could move that task, and then you have another extra node. You can, again, re-scale down the cluster. And now you have this arrangement where you're paying for less and getting higher density out of your cluster. So why would people use the spread algorithm then? Well, the main reason is there's less impact when a particular node dies. That's pretty a logical conclusion. Each node is trying to, the cluster scheduler is trying to spread load out onto as many nodes in the cluster as possible, so you expect each node to be running less jobs than under spread. Well, if you remember, we have one more rancor to go through, the job Anti Affinity. What we do with this is we actually kind of reap the benefit of the spread while maintaining the higher density of bin packing. So the job Anti Affinity iterator does not filter nodes. All it does is it applies a negative score to nodes that would be co-locating instances of the same job. So visually what that looks like is the rancor has annotated these two nodes, both of them can fit it, and the node that has the higher density has a higher score. So this one has a score of 13 and the next one has 9. But what the job Anti Affinity iterator will do is when it passes through, it'll detect that this job is actually running two of the same job, those two green nodes. So it'll apply a negative score because it realizes, hey, this is a service job. If this node goes down, your service might be negatively impacted. So I want to avoid, where possible, putting two together. So when the next one goes through, it doesn't have this problem. So it gets an unmodified score. So the job anti-affinity will only do a negative impact. And what we see is by the end, this node, even though it has lower density, the scheduler will go ahead and pick this because it avoids the co-location problem. Cool. So we're almost through the stack. The last one is the limit selector. What it does is it picks the highest scored node using sampling. So at a high level, what you can see is every node has gone through the full stack, so we only have eligible nodes. It's gone through the rankers, so they've been annotated. And the scheduler, if you remember, just calls select on the whole stack, and the output is the highest ranked node. So what this would do, obviously, is go through all the nodes and pick the highest one. So it would pick 17. That's conceptually what we do, not quite how it's implemented. And the reason is ranking is costly. The reason ranking is costly is each placement must go through each iterator, and you can't do this in parallel. Because as I decide to do one placement, as we saw, it can both impact the bin packing and anti-affinity score when it gets to the ranker, but it also can break your constraints. You might do it in parallel and both decide to, hey, let's use the same node, but that node might have this be in the same rack, and now you've broken your constraint. So you must do the placements in sequential order. So what we do is for batch jobs, we use a technique called power of two choices. So what the limit selector will do is actually only look at two nodes, and it'll pick the highest rank of just the two nodes. So in this case, it would pick a rank of 14, which was, it's not the max score possible given looking at every node, but it's pretty high. The reason we can get away with this is an insight that originally came out of load balancing research. It's called the power of two choices. The concept is if you have n balls that are placed into n buckets, if you do it at random, the maximum load or number of balls in a particular bucket would be, with high probability, log over log log n. But the insight is if you choose sequentially, and instead of picking randomly, you look at D bins, and you pick the least loaded of those D bins, you kind of inverse this. You get log log on the numerator and log D with your bins. So D of 2 actually yields an exponential improvement. So by just looking at 2, you exponentially make better choices. So this was, as I mentioned, originally from load balancing research. The first scheduler to apply this was the Sparrow Scheduler out of Berkeley. The Berkeley group that put this out is Amp Labs. They've done a lot of good work, so I've linked the Sparrow talk. They did a really good job, and if you want to learn more, there's also the link to the original paper that popularized this in load balancing. So we do a similar thing for services. Instead of 2, well, services, we expect them to exist in the cluster for a very long time, so we want a higher score where possible. We want to pick better nodes, so we're willing to spend a little more cycles deciding what node to pick. So what we do is of all the eligible nodes we started in that node source, we'll look at a log of them. And because of the behavior of the look ahead of the D buckets, you actually very quickly approach the optimal. So you approach the behavior of actually scanning every node and picking the best one. So we went through all of that for a single placement. The crazy thing is Nomad does this millions of times a second in a distributed fashion, and we ensure that it's correct and works every time. But how we do that is for a different talk. So I'll end with that and leave a little highlights for the next release, which will be coming out in the next couple of weeks or a month. So the 2 highlights I want to pull out are rolling deploys with health checks. So we'll, out of the gate, support console health checks. So when you deploy, it'll wait for it to come up and be healthy and be up and healthy for a configurable amount of time before moving through. You can also do manual triggers. So if you have more complicated control schemes and you're looking at 8 p.m. and then you only decide once things are looking good, you can also do that. Another one, in 0.5, we brought console template support native in the job file, so you could embed dynamic templates. People also really want to inject dynamic environment variables, so we're going to be extending that so you can send secrets through Vault or configurations from console through to your app using environment variables. And there's a lot more. I just pulled out 2 highlights. Thank you very much. I hope you guys enjoyed.